everyone. Let's solve a problem from GATE 2023 Aerospace Engineering question number 15. The question is, consider the Blazier solution of the incompressible laminar flat plate boundary layer. Among the following options, select the correct relation for the development of the momentum thickness theta with the distance x from the leading edge along the length of the plate. Okay, so we have been given four options for relation between the momentum thickness and the distance from the leading edge of the plate. So let's solve this problem. The NPTEL video reference for this particular question would be, the course is the Introduction to Boundary Layers by Professor Rinku Mukherjee from IIT Madras. You can see the course webpage link here. And then the particular video that we want to refer to this question is week number 2 on module 6, which is concepts of boundary layer displacement thickness and boundary layer momentum thickness. And you can also see the YouTube link for the particular video. Let's solve the problem. Let's start with the flat plate where the boundary layer is getting developed. So this is the flat plate that we are having a look at. So flat plate, right? So and this is the leading edge of the plate. We have been given, we have to take the distance from the leading edge, right? So at the leading edge, the distance x is equal to 0. So if you are taking the coordinates to be x along the streamwise direction, y perpendicular to the streamwise direction, and the leading edge, at the leading edge x is equal to 0, and along the leading edge the boundary layer will develop, right? So let's draw the free stream as well, and the free stream flow will come in this direction with the velocity of u infinity, which is free stream velocity, right? So once the free flow touches the plate, a boundary layer will form, right? So boundary layer will form. So this is the boundary layer that is formed on the flat plate, right? So how the velocity profile will look like inside the boundary layer? So the boundary layer, so the velocity at the flat plate, at the flat plate would be 0, and it will start increasing, right? It will start increasing and it will become constant after the edge of the boundary layer, right? It will start increasing and it will become constant at the edge of the boundary layer, right? Here it will become u infinity. So u varies along the y direction, right? So it varies from 0 to u infinity. At particular distance, at a far away distance from the plate, the velocity will become the free stream velocity. That is the concept, right? Okay, let's we have been asked to consider the Blazier solution for this question, right? So let's write the Blazier solution, Blazier's equation. So proposed by the Blazier's, f triple dash plus f double dash equal to 0. Okay, here we use a similarity solution for this. Here we take eta is equal to y by delta, and which is delta will be taken as y into u infinity by eta x, okay, and f dash is taken as u by u infinity, right? So we are taking these similarity variables and trying to solve the momentum equation, and we end up in this equation, okay? So which will have the boundary condition as to be, the normal boundary condition for this will be u and v will be 0 at y is equal to 0, right? That will come out to be f comma f dash will be 0 at I is equal to 0, and u will tend to u infinity as y tends to infinity, right? At y tends to infinity, we already told that u will become the free stream velocity. So then f dash will become 1 as eta tends to infinity, right? So this is what we have. Let's write this to be equation 1, the equation and the boundary condition. Now let's go to the actual question of the problem, which is the momentum thickness. I'll write the formula for the momentum thickness: 0 to infinity, that is 0 till the infinity, that's what we represent here, by u infinity minus 1 minus 1 minus u by u infinity dy, right? So now let's write f dash instead of u by u infinity. So then what we'll get: 0 to infinity f dash 1 minus f dash. So we have to convert this y into eta, right? So when we differentiate this, and we will get um, eta x by u infinity into d eta. So all this will be constant. This is not a function of eta. So then let's take all of this to be outside. Eta by u infinity 0 to infinity f dash minus f dash square d eta, right? So this is what we have, and the problem here is to solve the f dash square. Okay, so let's see how to integrate this f dash square with respect to eta. So we know the problem, so we have to integrate f dash square. So let's write this to be f dash and f dash. Okay, so and we got a format of uv dash, right? So I'll write that formula for you, and which is integration of u dv will become uv minus v du. It's the formula, right? Here we are taking u to be f dash and dv to be f dash d eta. Okay, so if we want du, then that will become f double dash, differentiation, right? And if we want v from this, it will become f. Okay, so let's substitute everything in this equation. We have to, which is uv, then this will become u is f dash and v is f minus integration of v is, we have f du, right? So du is f double dash, right? So f double dash. If you see this format, f and f dash, you can see from f and f dash here. So you can substitute this f and instead of f dash to be minus 2 f triple dash, right? So from the equation 1, this comes out to be minus 2 f triple dash, right? This f dash. So let's write f dash f, minus into minus will become plus f triple dash d eta. Okay, so you have to integrate f triple dash, that has become now ec f dash f plus 2 f double dash, right? So this is what we get for integrating f dash square. Okay, so now let's substitute this here. We'll get x by u infinity. If we integrate f dash, we'll get f. We have to substitute the limits of the integration. This is 0 to infinity minus f dash f. I'm writing this one, f dash f of 0 to infinity minus 2 f double dash from 0 to infinity, right? Right, infinity here. Okay. So if we substitute the limits, x value infinity, this will become f infinity minus f0. Just writing f at eta is equal to infinity and f at eta is equal to 0. Okay, that's what it means. Again, f dash f at infinity plus f dash f at 0 minus 2 into f double dash infinity minus f double dash 0, right? So this is what we have. So we need to know all this boundary condition. Let's take it from this boundary condition and try to solve these. Okay, so okay, so f at infinity, that we don't have a boundary condition here. Okay, let's keep it as it is. And f at 0, let's see, f at 0 at eta is equal to 0, f will become 0, right? This will become 0 from 1, equation 1, right? And again, f and f dash will become 0 at eta is equal to 0. This is from equation 1. Okay. Now, and at eta tends to infinity, f dash becomes 1, right? This will become to be 1, right? Now what do we have? Now we have x u infinity f infinity minus f infinity minus 2 into f double dash infinity minus f double dash 0, right? Right. So this 2 will get cancelled and we'll have some value here. So we do not know what is f double dash at infinity and f double dash at 0. So this can be obtained by numerical computation, but we know we don't need that here. You can just for the sake of completion, I'll just write the values, but the numerical computation, from the numerical computation you will get around this value to be 0.3321 and this value to be 0. Okay, so all of this is a numerical value, right? So this is theta. So what do we have? We have to relate only x, right? So we have x. For the sake of completion, I have solved the complete problem, but you can just get this directly here. If you just take this equation, all of this will come out to be some value, right? Some numerical value. We don't have a function of x here, so we just have a root x here. You can just directly take from this step, or instead it can be solved until the last moment and to see how the momentum thickness varies, right, to get actual equation. So then the actual equation that we get for the momentum thickness will be 0.664 y u infinity, right? So this is the final form that we will get if we substitute this equation, right? So that's all for this question. Thank you.